Assalamu alaikum, dear students. Today our topic is general trends in the properties of the block elements. So we will discuss today the three properties which are atomic and ionic radii, metallic character, number third is ionization, enthalpy, or ionization energy. Now, we'll take the first property, that is atomic and ionic radii. Before discussing the atomic and the ionic radii of these transition elements, I will write the first transition series, that is 3D series. The elements of the 3D series are: first transition, series or 3D series. It is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. And also I will write the atomic numbers are 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And here we have, these are the transition elements or D block elements. And here we have P block elements. And here we have S block elements. So before these we have beryllium, magnesium, calcium, strontium, barium, and radium. And here we have boron, aluminium, gallium, andinium, thallium. This is 31. 5, 13, 31, and accordingly you will add 8, 32, 18 and 32. This is 3, 11, 20. this is 21, then this is 20 and 18, 38, we will add 18, we will add 32. Now the atomic radii of the transition elements lies in between the S block elements and the P block elements, and along the series the atomic radii of these transition elements decrease along the series. That means scandium has higher atomic radii than titanium, accordingly it will decrease. Similarly, the trend is followed by 4d, 5d series of the transition elements. Let us take the 3d series, and in the 3d series the atomic radii decreases from scandium to zinc, although it remains the decrease in the atomic radii is very small from the midway. Now, and at the last it slightly increases. Now, atomic radii, why the atomic radii decreases? It is the decrease in the atomic radii along the series is due to the increase in the atomic number, and when the atomic number increases, the nuclear charge also increases. This is why, due to the increase in the nuclear charge, the addition of the electron goes to the same outermost shell, and with the increase in the nuclear charge, increases the attraction of the outermost shell electrons. This is why the size decreases, atomic radii decreases. Now, why this trend? Why there is small decrease from manganese to copper, and why there is slight increase from copper to zinc? It is because that initially we don't have the electrons do not enter the d subshells, and with the addition of the electron in the penultimate d subshell, the shielding effect increases, and this shielding effect of the electrons to the outer shell electrons from the nuclear charge, that affects the size. This is why the size of these from manganese to copper shows a slight decrease. And why there is increase in the atomic radii from copper to zinc? It is because the filling in the zinc, the penultimate d subshell is completely filled, and due to the electron repulsion in the d orbital, in all the orbitals of the d subshell, the force of the repulsion exceeds the nuclear force of the attraction. This is why that electron cloud increases here in case of the zinc, and it shows a slight increase in the atomic radii. The trend remains the same for the ionic radii. That means the ionic radii also decreases along the series. And if we move down the group, the atomic radii increases due to increase in the number of shells, due to the increase in the atomic number, due to the increase due to the increase of the number of shells. So this is all about atomic and ionic radii. Now the second is metallic character. Except mercury, which is liquid, all the transition elements show a peculiar metallic or typical metallic structure. They possess all the characteristics of metals. That is, they are hard, lustrous, have high melting and boiling points, are malleable and ductile, have high thermal and electrical conductivity, and tensile strength. So these transition elements or the D block elements, they show the metallic character. It is because their outermost shell, that is their general outer shell electronic configuration, is ns1 to 2, n-1, d1 to 10 electronic configuration. It is sometimes we have 0 to 2 electronic configuration. That means their outermost shell electrons are ns electrons, and the outermost shell electrons contain either 1 or 2 electrons in the s subshell. So these s electrons form the metallic bonds with other elements, due to which these transition elements show metallic character. Not only these n-1, d1 to 10 electrons, that is in the penultimate shell, they also form the metallic bonds. That means both ns and n-1d subshells, electrons of these two subshells, contribute towards the formation of the metallic bonds. And greater the number of unpaired electrons, in the D subshell, greater is the stronger is the bonding, and more strong are the transition metals. This is why the manganese, and lesser the number of unpaired electrons, weaker is the bonding, because in case of maximum number of the unpaired electrons, bonding is strong because there is overlapping of these, maximum overlapping of these unpaired electrons. This is why we have chromium, molybdenum and tungsten. They are very strong transition metals. This is why, because they have maximum number of the unpaired electrons, and zinc is not very strong metal because it has no unpaired electron, d electron. This is why zinc or cadmium or mercury, they are not very strong metals. It is because their outermost shell is, we have, for the zinc we have 3d10,4s2 electronic configuration. Similarly, for cadmium we have 4d10, 3d10,4s2, we have 4d10, 5s2. Similarly, we have 5d10, 6s2 electronic configuration for zinc, cadmium and mercury. That means they have no unpaired electron. This is why while forming the bond there is not stronger bonding due to the absence of the unpaired electrons. So this was all about the metallic character. Now we have the ionization enthalpy or the ionization energy, and for this, to understand the ionization enthalpy, we have to write the outer shell electronic configuration of these elements. Let's take the ionization enthalpy or energy of first transition series, that is 3D series. We have the second, we have, it is electronic, outer shell electronic configuration is 3D1 4s2, just as we have discussed it in the previous lecture, and we have 3D2 4s2. It is electronic configuration is 3D3 4s2, and chromium it is 3D5 4s1, and manganese it is 3D5 4s2, iron it is 3D6 4s2, cobalt 3D7 4s2, nickel 3D8 4s2, copper it is 3D10 4s2, and for zinc we have, its electronic configuration is 3D, it is 3D10 4s1, sorry, and it is 3D10 4s2. Now, what is ionization enthalpy? Or ionization energy. Ionization enthalpy can be defined, it is the amount of the energy required to remove the most loosely bound electron from the gaseous neutral atom. So if we remove one electron, that is called first ionization energy. We denote the ionization energy IE, and if we remove the one electron, that we denote by IE first ionization enthalpy. Now, the ionization enthalpy of these D block elements, that is, it is greater than S block elements, and it is lesser than P block elements. That means the ionization enthalpy of the D block elements or the transition elements lies in between the S block elements and the P block elements. S block elements on the left of the transition elements and the P block elements on the right of these transition elements or D block elements. The ionization enthalpy of these D block elements is greater. That means the S block elements have smaller ionization enthalpy than these D block elements. And the ionization enthalpy of these D block elements is smaller than P block elements. And this ionization enthalpy is the amount of energy required to remove the most loosely bound electron. So, along the series, the ionization enthalpy, that means as the size goes on decreasing, the ionization enthalpy increases. There is increase in the ionization enthalpy. Now, for the first, and similarly we have trends for ionization enthalpy of 4D and 5D series increases, transition series increases along the series. That means the ionization enthalpy of the titanium is greater than scandium, vanadium is greater than titanium, but there are some exceptions. So, ionization enthalpy increases along the series. So, this is the increasing order of the ionization enthalpy. But this electronic configuration plays a very important role in determining the ionization enthalpy of these elements. Suppose we are here taking the first transition series elements. The ionization enthalpy of it must increase, but the ionization enthalpy of manganese, if we say this is manganese, we have to remove the electron here. We have to remove the electron from the exactly half-filled electron and completely filled electron. That means the trend increases, but here in case of the zinc, we have to remove the electron against the completely filled D and S orbitals. So, no doubt the ionization enthalpy increases, i.e. first increases along the series, but it for the zinc, the ionization enthalpy of zinc, first ionization enthalpy of the zinc is very, very high as compared to the rest of the elements. It is because it has the completely filled configuration, because we have D10S2 configuration, 3D10 4S2 configuration for the zinc, and we have to remove the electron again as the most stable configuration of D10 and S2. This is why the first ionization enthalpy of the zinc is higher than that of the rest of the, is very high as compared to that of the rest of the elements. If we take the second ionization enthalpy, that is IE2, IE2 means we have already removed the first electron from these outermost shell electrons. That means here we have scandium. When we have removed the one electron, we have scandium first here, Se plus, and we have, instead of 3d1 4s2, we now have 3d1 4s1 electron. Similarly, we have 3d2 4s1, 3d3 4s1, 3d5 4s1, and 3d5 4s2, 3d6 4s2. So first electron when we have removed, that means 3d1 4s here, it now becomes 3d5 here. After we have removed the first electron, the chromium plus it, IE first, we have to remove the electron against the 3d5, and here for the manganese it will be 3d5. When we have removed the first electron, its electronic configuration will remain 4s1. So now we have to remove the electron. We have to here remove the electron against the most stable, it is the exactly half-filled orbital, and we have to remove the electron. That means we have to apply the more energy to remove the electron because it is stable configuration. Then this we have to remove against, it becomes the stable after removing the 4s electron. That means here the electronic configuration of the chromium Cr first IE second जो है, the chromium is, it must increase. Here it is manganese, it is 3d5 4s1 3d and 3d. Here the smaller energy, we have to apply the smaller energy because after removing this electron it also remains the stable configuration. So here the ionization enthalpy of 3d5, that is chromium first, is higher than IE second, for chromium is greater than that of the manganese, that of IE2 of manganese. क्लियर? मेरी बात समझ आ गई होगी कि 3d IE second जो है क्रोमियम का, वी हैव टू रिमूव द क्रोमियम. अब हमें जो इलेक्ट्रॉन रिमूव करना है वो 3d5 से रिमूव करना है, और इन केस ऑफ द मैग्नीज हमें जो इलेक्ट्रॉन रिमूव करना है वो 3d5 4s1 कन्फिगरेशन से रिमूव करना है. तो it becomes easy to remove the electron from 4s1 because it still remains the stable configuration. It still remains exactly half-filled, whereas here we have to apply more energy to remove the more stable configuration so that its configuration will become 3d4. So, तो यहाँ पर ये बात, यहाँ मैग्नीज को जो ट्रेंड से डिविएशन हो गई, मैग्नीज को ज्यादा IE सेकंड होनी चाहिए क्रोमियम से, लेकिन क्रोमियम सेकंड, IE सेकंड फ्रॉम क्रोमियम इज ग्रेटर देन IE सेकंड फॉर द मैग्नीज. Similarly, if we take here, after removing the one electron, the IE second, IE first में अब कॉपर का इलेक्ट्रॉनिक कन्फिगरेशन जो रहता है वो 3d10 रहता है, और जिंक का जो रहता है 3d10 4s1 है. तो दिस फॉर जिंक. जब हम दूसरा इलेक्ट्रॉन रिमूव करेंगे, यहाँ 4s से हमें रिमूव करना है, गो कि दोनों स्टेबल है 3d10 4s1, बट आफ्टर रिमूविंग द इलेक्ट्रॉन फ्रॉम 4s1 तब भी हमें स्टेबल 3d10 इलेक्ट्रॉनिक कन्फिगरेशन रहता है फॉर द जिंक, वायर एज कॉपर के लिए वी हैव टू रिमूव द इलेक्ट्रॉन फ्रॉम द मोस्ट स्टेबल 3d10 configuration. So we have to apply the more energy, so the IE second for copper is greater than zinc. होना ये चाहिए था कि जिंक का ज्यादा होना चाहिए अकॉर्डिंग टू द ट्रेंड फ्रॉम कॉपर, लेकिन कॉपर का ज्यादा है फ्रॉम द जिंक. तो दिस वाज हाउ वी determine the ionization enthalpy of IE first or IE second. For understanding that this ionization enthalpy, you must remember the electronic configuration कि इलेक्ट्रॉन रिमूव करने से इसकी कन्फिगरेशन जो है वो कैसी रहती है. इफ इट इज रिमेन स्टेबल देन लेसर अमाउंट ऑफ द एनर्जी इज रिक्वायर्ड टू रिमूव दैट इलेक्ट्रॉन. अगर इलेक्ट्रॉन हमें रिमूव करना है फ्रॉम द स्टेबल कन्फिगरेशन, देन मोर एनर्जी इज रिक्वायर्ड टू रिमूव द इलेक्ट्रॉन फ्रॉम दैट कन्फिगरेशन. अब अगर I3 हम ले लेते तो I3 के लिए ionization enthalpy we have to remove the third electron. तो थर्ड इलेक्ट्रॉन कैसे आप रिमूव करोगे? ये हम ले लेंगे क्रोमियम मैग्नीज और सपोज वी विल टेक नाउ आयरन. For removing the I first for iron will be 3d6 4s. आई फर्स्ट में इसका कन्फिग्रेशन 4s1 रहेगा. आई सेकंड में इसका कन्फिग्रेशन आई सेकंड में 3d6 रहेगा. एंड आई थ्री में इसका कन्फिग्रेशन वो 3d5 रहेगा. सो इसके बरक्स अगर हम ले लेंगे मैग्नीज, तो मैग्नीज का इलेक्ट्रॉनिक कन्फिग्रेशन आई फर्स्ट में मैग्नीज, ये आयरन है एंड दिस इज मैग्नीज. नाउ तो मैग्नीज का आई फर्स्ट में इलेक्ट्रॉनिक कन्फिग्रेशन रहेगा 3d5 4s1. आई सेकंड में 3d5 4s तो रहेगा ही नहीं. नाउ फॉर I3 we have to remove the electron from 3d6, and here we have to remove the electron from 3d5 to become 3d4. अब इन दो में कौन स्टेबल कन्फिग्रेशन है? 3d5 is more stable electronic configuration. It is this configuration we have to remove the electron from more stable, because it is exactly half filled. We have to remove the electron from the stable configuration so that it becomes 3d4, because either the subshells must, your orbitals must be completely filled or completely half filled. So this is exactly half filled configuration. So when we are removing the electron from 3d5 configuration to form the 3d4 configuration, we have to apply more energy. Instead हम 3d6 से इलेक्ट्रॉन रिमूव करते हैं. 3d6 से इलेक्ट्रॉन रिमूव करना आसान है क्योंकि 3d5 is more stable configuration than 3d6. So the I3 for iron is smaller than IE3 for manganese. So this is the deviation जो हमें increasing order में ionization enthalpy होती है along the series. So these were some of the deviations in the general trend of the ionization enthalpies.